Hello, everyone. Welcome once again into our channel, Making Life Easier, and on our series on basic mechanics. In our last video, we look at how to find the components of a force in 3D using angles. Today, we are going to find the components of a force in 3D using distances. Kindly subscribe to our channel, like and share, and hit the notification button as well. Quickly, let's look at our next question, which is example 2. In the figure below, if the magnitude of the force is 300 newtons, determine the components of the force. So we have been given the force, we have been given the distances on the 3D object, and we are asked to determine the components of the force. Let's quickly look at how to solve this problem. Good. In our last video, or in our previous video on resolving forces into components, we explained that anytime you are given a 3D object or a force which is in 3 dimensions and you are asked to resolve, the formula is F bar is equal to the scalar force which you are given times lambda. And we explained that lambda is obtained by 3 ways. 1, using angles. Number 2, using distances. Number 3, using forces. We explained this in our previous video. Kindly go back to our previous video and familiarize yourself with the formulas which are used in all these 3 instances. Now, in this video, because we are not giving, in this question, because we are not giving the angles, we are not giving the angles the force makes with the X, we don't know the angle the force makes with the Y, and we also don't know the angle the force makes with the Z. So in this type of question, but you have been given the distance on the distances on the 3D object. So it means that we can be able to solve this problem using distances. So quickly, let's look at how to solve this question. We know that our F is equal to F lambda. And then we said that when you are solving, if you want to get the direction cosine, this is the direction cosine. Because we said that it indicates the direction of the force. So if you want to get our lambda, which is the direction cosine, using distances, then our formula is going to be lambda equals the distance in the x-axis, the xi, plus the distance in the y-axis, which is the yj, plus the distance in the z-axis, which is the zk, all over d. And in this case, our d will be the magnitude of all the individual distances here, which we know that the magnitude is going to be the square root of the distance in the s squared plus the distance in the y squared plus the distance in the z squared. So this will give us our d. So once we have been able to get this d and we know the distance the force is moving on the x, the distance the force is moving on the y, and the distance the force is moving on the z, we should be able to get our force in the vector form or the force in the component form. Now, looking at this object, don't forget that we have already established the fact that the force always has a point of application, and so the point of application is at this side, and from this diagram, the force is ending at this side. So always we need to determine the distance from where the force has been applied. So the point of application is very important. That is where we are going to start our measurement from. That is where we are going to start our measurement from. So it means that in this question, if we want to move from this point where our force has started from to this point where our force is ending, we need to move around our box. We need to move around our box and get the distances. So from this point, you can see that if we want to move from this point here to this point here, now we need to move along the box. So we are going to move this distance here. We are going to move this distance here. And then also when we reach this point, we are also going to move this distance here. And then from here, we are also going to move this distance up like that before we get to this point. So now let's establish the fact that our unit vectors are in this format. Our unit vectors are in this format. This is on the y-axis, our unit vector is j. And on our z-axis, our unit vector is k. And on our x-axis, our unit vector is r. So it means that if our unit vector is if we are moving in the same direction with our unit vectors here, then our distance is going to be positive. If we are moving in the opposite direction, so here you can see that on the y-axis, our unit vector is moving up. So it means that when we are moving around this diagram, anytime we are moving upwards, our distance is going to be positive. However, if we are moving downwards, then our distance is going to be negative. Our distance is going to be negative. In the same way, anytime we are moving this direction on the z-axis, our distance is going to be positive. And when we are moving in the opposite direction, like this, if we are moving in the opposite direction, then our distance is going to be negative. On the x-axis, anytime we are moving this way, this direction, then our distance is going to be positive. But if we are moving in the opposite direction like this, from our I, then it's going to be negative I. Take note of this because we are going to apply this in determining our distances. So, having been able to establish that, let's see, if we are moving from this point, you can see that this distance here is along the x-axis. This distance here is along the x-axis. And look at our direction. We are moving in the same direction with our x. This is the direction of the x. Don't forget that we said that if we are moving this direction, it's going to be positive. So from here, we are moving this direction, which is in the same direction with our unit vector I here. So it means that this distance here, which is representing x, is going to be positive. So our 200 millimeters is going to be positive. But let's change our 200 millimeter to meters. So it means that from here we can say that the distance of the force, let's take it that our force, the vector force, when we want to move from this point O to this point F, we are going to move this distance on the x, which we are saying that it will be in the same direction with our unit vector I. So it's going to be positive. So we are going to get 0.2 meters, but it's in the I direction. So we represent it with I. Plus, from this point, we also move this direction. We move this direction on the Z. We will move this direction on the Z. This direction on the Z. But from the diagram, our unit vector Z is going this direction. Is going this direction, but we are rather moving in the opposite direction. So it means that our distance there is going to be negative because you are moving in the opposite direction to our Z. So it means that on the Z axis, we are going to get our distance as negative 0.5 meter. It's on the Z axis, so we are going to give it the unit vector A. Then from here, we are going to move up. We are going to move up before we can get to point F. We are going to move up. And we are saying that anytime we are moving up on the y-axis, it's positive. So it means that our distance there, when we change this to meter, will be 0.35 meter J. That one will be positive. So once you have been able to get this, these are what is up here. These are what is up here. So we need to determine our D. And we are saying that our D is always the square root of whatever is there. So the square of this plus the square of that plus the square of this, which is negative 0.5 squared. And from there, our D will be equal to 0.642. And once you have gotten that, then we can be able to determine our lambda. So from here, our lambda, which is the direction cosine, will be equal to 0.2i plus 0.35g minus 0.5a all over our D, which is 0.642. And from here, our lambda will be equal to 0.312i. That we will do them separately because this is I, this is J, this is K, so we cannot put them together. So we do 0.2 over this, 0.35 over that, and 0.5 over that. So we are going to get 0.312 plus 0.545 minus 0.779. We have gotten our direction cosine now. So from there, we can quickly get our force in the component form or in the vector form. Our force will be equal to, in the component form, will be equal to the magnitude of our force, which is scalar. So the magnitude of our force, which is scalar, is 300 newtons. We are going to get 300 into bracket our lambda, which is 0.312i plus 0.545g, and then minus 0.779k. Then from here, we can simply get our F. Our F will be equal to 93.6i, which represents the S component of our force, then 163.5g, which represents the Y component of our force, and negative 233.7, which represents the Z component. So this represents our F of X, this represents our F of Y, and this represents our F of Z. So now we have been able to represent our force in the component form or in the vector form. So this is how you can be able to determine the force in the component form using the distances, on the x-axis, the distance on the y-axis, and the distance on the z-axis. And this is very simple. This is very simple, and then we can all go through easily. So if there is anything which you don't understand, or if there is anything you need clarification on, you can kindly alert us at the comment section, or if you have any suggestion for us also, you can make us know at the comment section. Once again, thank you very much for watching. Kindly subscribe to our channel, like, comment, and share as well. See you again for our next video. Bye-bye. Thank you for watching.